Welcome to this lesson on moment of inertia, also known as rotational mass. This is a fundamental concept in rotational motion that helps us understand how objects behave when they spin or rotate. Just like mass tells us how hard it is to push something in a straight line, moment of inertia tells us how hard it is to make something start spinning or stop spinning. Moment of inertia is the resistance of an object to rotational acceleration about an axis. Think of it this way. In linear motion, mass resists acceleration when you push an object. Similarly, in rotational motion, moment of inertia resists rotational acceleration when you try to spin an object. It's the rotational equivalent of mass. The greater the moment of inertia, the harder it is to change how fast something is rotating. The formula for moment of inertia is I equals the sum of m sub I times r sub I squared. Let's break this down. I represents the moment of inertia itself. M sub I is the mass of each individual particle in the object. R sub I is the distance of that particle from the axis of rotation. The Greek letter sigma means we sum this up for all particles in the object. Notice that distance is squared, which makes it very important in determining the moment of inertia. Here's a crucial insight. Distance from the axis is squared in the formula. This means that mass located farther from the axis contributes much more to the rotational inertia than mass close to the axis. For example, if you double the distance of a mass from the axis, its contribution to moment of inertia increases by a factor of 4. This squared relationship makes the distribution of mass extremely important in rotational motion. Let's look at the simplest case, a single point mass. For one mass at distance r from the axis, the moment of inertia is simply I equals mr squared. When we have multiple point masses, we use the full formula. I equals the sum of m sub I times r sub I squared. We calculate the contribution from each mass separately, then add them all together to get the total moment of inertia of the system. 4 main factors affect moment of inertia. First, total mass. More mass means greater moment of inertia. Second, mass distribution. How the mass is spread relative to the axis matters tremendously. Third, axis location. The moment of inertia depends on which axis you choose for rotation. And fourth, object shape. The geometry of the object determines how mass is distributed, which directly affects the moment of inertia. Different shapes have different formulas for moment of inertia. A solid cylinder rotating about its central axis has moment of inertia equal to 1/2 mr squared. A hollow cylinder about the same axis has moment of inertia mr squared. A solid sphere rotating through its center has moment of inertia equal to 2/5 mr squared. And a thin rod rotating through its center has moment of inertia equal to 1/12 ml squared, where L is the length of the rod. The Parallel Axis Theorem is a powerful tool for calculating moment of inertia. It states that I equals I sub cm plus md squared. I sub cm is the moment of inertia about the center of mass, and d is the distance between the center of mass axis and the new parallel axis. This theorem allows us to calculate the moment of inertia about any parallel axis, as long as we know the moment of inertia about the center of mass. Moment of inertia plays a central role in rotational dynamics through Newton's second law for rotation. Torque equals I times alpha. This equation shows that torque causes angular acceleration. The key insight is that for the same applied torque, a larger moment of inertia results in smaller angular acceleration. This is exactly analogous to how in linear motion, a larger mass results in smaller linear acceleration for the same applied force. Let's summarize the key points. Moment of inertia is the rotational equivalent of mass in linear motion. Distance from the axis matters more than mass itself because of the r squared factor in the formula. The value depends on both the axis location and how mass is distributed around that axis. Finally, moment of inertia controls how easily objects start or stop rotating. Understanding these principles is essential for analyzing any rotational motion problem in physics.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.